Welcome back to the deep dive. Today we've got a mission tailored specifically for you.
Yeah, especially if you're prepping for a hardware design meeting or honestly just insanely curious about the hidden infrastructure of the modern world.
Exactly. It's going to be right up your alley. We are going to decode a hidden language.
Yeah.
And the wildest part about this is that this language is hiding in plain sight inside almost every single electronic device on planet Earth.
Right, whether it's the smartphone in your pocket, the laptop on your desk, or, the microwave in your kitchen.
This secret code is etched right into its core. To do this, we're pulling from a really comprehensive breakdown of something called the RKM code, directly from our Wikipedia source material.
And it's a topic that seems incredibly niche at first glance. But once you begin to unravel it, you start to realize how the smallest, seemingly insignificant logistical decisions can fundamentally shape global manufacturing for decades.
It really connects physical engineering with pure data management.
It does. It's a fantastic subject to dig into.
It really is. So let me ask you this. Have you ever cracked open a broken radio?
Oh, yeah.
Or maybe taken apart an old remote control when you were a kid? Or perhaps you just look really closely at a computer motherboard?
If you have, you've definitely noticed those tiny little rectangular components.
Right, the resistors, capacitors, inductors, all soldered onto the green fiberglass board. And if you squinted hard enough, you might have seen some very cryptic alphanumeric codes printed on them.
Something like 4R7 or 47K.
Yeah. And at first glance, it almost looks like a factory typo. You might wonder, why don't engineers just print standard numbers in units? Why not just write 4.7 ohms? Okay, let's unpack this. Why are we dealing with cryptic letters instead of plain numbers?
What's fascinating here is that this notation isn't just some random manufacturer's quirk
Right.
or a misprint on a particular assembly line. It's a rigorously defined, globally recognized shorthand.
That's standard.
Exactly, standardized by the International Electrotechnical Commission, specifically in a standard known as IEC 60062, all the way back in 1952.
Wow, 1952.
Yeah, so we aren't looking at some new internet-age tech speak here. This is a system that has been governing electronics since the early days of the Cold War.
That really puts things in perspective. And according to the source material, this entire global standard stems from a very real, very physical problem.
The dot.
The problem with the dot, the standard decimal point. Imagine you're manufacturing a microscopic resistor, and you need to print its resistance value on the side.
Say the value is 4.7 ohms.
Right. To do that, you have to print a tiny number 4, a microscopic dot, and a tiny number 7. In the physical world, on a component that might be the size of a grain of rice,
Or even smaller.
or even smaller, that decimal point is your absolute worst enemy.
Because a single dot of ink is incredibly fragile. On a factory floor, these components are tumbling through sorting machines.
They're being grabbed by robotic arms.
Or handled by technicians with grease on their gloves. A tiny scratch, a bit of wear and tear, or just a slightly misaligned print job, and that microscopic decimal point easily rubs right off the component.
Which completely changes the value of the part if you're trying to read it later. But the source notes, it isn't just about the physical components, right?
Yeah.
The documentation is where this gets truly disastrous.
Precisely. The vulnerability of the decimal point was a major problem in the engineering office itself. Think about how information moved in the 1950s, 60s, and 70s.
Circuit diagrams were drawn by hand.
Right, and then they were constantly being photocopied, duplicated, and faxed across the world. Decimal points have a notorious habit of completely disappearing when schematics are photocopied multiple times.
A speck of dust on the copier glass, low-resolution toner, a coffee stain, and poof.
The dot is gone.
And losing a decimal point on a schematic isn't just a minor typo that you can brush off.
Not at all. If you lose the decimal point on a diagram calling for a 4.7 ohm resistor, the next person down the line reads it as a 47 ohm resistor.
That is 10 times the intended electrical resistance.
10 times. If a technician builds a circuit based on that faulty, degraded photocopy, the entire circuit could malfunction. Depending on the application, it could overheat, blow a fuse, or literally catch fire.
The stakes were surprisingly high for a tiny, vulnerable dot of ink.
They really were.
So the engineering world needed a bulletproof way to write these numbers that could survive terrible photocopiers and greasy fingers. And the elegant solution they came up with in the RKM code is brilliant in its simplicity.
It is.
You take that fragile, vulnerable decimal point and you completely eliminate it. Instead, you replace it with a sturdy, highly visible letter from the alphabet.
The letter acts as both the multiplier prefix and the decimal separator all at once.
Let me walk you through how this actually works, because visualizing it makes it click instantly.
It's a very clever typographical trick.
It really is. So let's take that same 4.7 ohm resistor. Instead of writing 4.7, the RKM code dictates you write 4R7.
The R drops right into the space where the dot used to be.
You literally cannot miss a giant capital R on a bad photocopy.
And it scales up depending on the value of the component.
Right, so if it's a larger value, say 4.7 kiloohms, the K becomes the decimal point. You write it as 4K7.
Makes sense.
And if you have a solid number where there is no decimal point needed, like 470 ohms, you just stick the letter at the end to confirm the value, making it 470R.
And for components requiring high precision, you might have trailing zeros. A value like 15.0 megohms uses the M for mega as the decimal marker, making it 15M0.
The system guarantees that an alphanumeric character is always anchoring the value, providing a visual failsafe.
Exactly.
That makes a lot of sense. But looking at these examples, something is conspicuously missing. In 4R7 or 15M0, there is no mention of the word ohm for resistance or farad for capacitance. The actual unit of measurement is just gone.
That is entirely by design. For the sake of brevity on these tiny surfaces, the code usually drops the actual unit names entirely.
You're just expected to know what unit you're dealing with.
Right, based on the physical appearance of the part you were holding and the specific letters being used. Which brings us to the very deliberate choices made regarding the alphabet.
Let's look at resistors first, since they make up the bulk of this. Resistors typically use uppercase letters.
Yeah.
So as we discussed, you see K for kilo, M for mega. I'd imagine G is for giga, and T is for tera.
That is correct. They follow the standard SI prefixes for the most part.
But wait, what about that R we used for basic ohms? The standard scientific symbol for ohms is the Greek letter omega. Everyone remembers that horseshoe shape from high school physics.
Oh, sure.
Why didn't they just use 4 omega 7?
This is a perfect example of how the technological limitations of an era dictate the standards we still use today. You have to remember the context of early computing, early typewriters, and early drafting systems.
Right, they didn't have special character menus.
The Greek letter omega was simply missing from most character encodings. It wasn't in early ASCII, and it certainly wasn't available in early CAD/CAM environments. That's computer-aided design and manufacturing.
You just couldn't type an omega on a standard keyboard.
No, or render it reliably on early cathode ray tube screens and dot matrix plotters.
So they were forced to find a stand-in from the standard Latin alphabet.
Exactly. The letter R was chosen for two very practical reasons. First, visually, a capital R looks a little bit like the omega glyph if you squint and use your imagination.
I can kind of see that.
But much more importantly, it serves as a fantastic mnemonic for the word resistance across several major languages. It was a pragmatic compromise when the ideal symbol was technologically unavailable.
A workaround for mid-century keyboards that we were still stamping onto modern microchips. That is amazing. Now, I was looking through the notes on the resistor alphabet, and I found this exception that threw me for a loop.
A L exception.
The L exception. Say you want to write a tiny resistance, something measured in milliohms. Milli means 10 to the power of -3. Normally, you'd use a lowercase m as the standard prefix.
But the RKM code insists on maintaining an uppercase-only rule for resistors to avoid visual clutter.
Right. And you obviously can't use a capital M for milli, because M is already permanently assigned to mega, which is a million ohms.
Mixing up a milliohm and a megaohm would be catastrophic in any circuit design.
Total opposite ends of the spectrum.
One is essentially a dead short, and the other is a massive roadblock to the current.
So to solve this clash, the code completely throws out the M and uses a capital L for milli instead. Why L?
It seems it just fits the uppercase requirement without clashing with the M for mega.
It shows how they were willing to abandon standard prefixes to protect the integrity of the code.
And that willingness to adapt led to some other, less ideal variations out in the wild.
You mean the E anomaly?
Mm.
I saw this rogue, non-standard variation in the source material.
Yeah.
Apparently, sometimes you will see a capital E used instead of an R for basic ohms.
Yes.
So a component might read 4E7 instead of 4R7. Where did that come from?
It is a fascinating historical holdover. The reason E was sometimes used is purely visual. A capital E looks quite a bit like a sideways, lowercase Greek omega. And historically, well before World War II, engineers actually used the lowercase omega to denote ohms before the uppercase omega became the universal standard.
Oh, I see. So it's an old school visual pun. They just rotated the letter in their minds.
It is. However, I must stress that this variation is strongly discouraged today.
Because it breaks things.
It causes massive headaches in modern computing. The problem is scientific E notation, which is standard on calculators and in programming languages.
Ah, right.
In that context, E stands for times 10 to the power of. So if a modern computer reads the string 4E7, it interprets that as 40 million, not 4.7.
Yikes.
It's a perfect storm of conflicting notations that can completely break automated design software.
Note to self, do not use E unless you want to completely confuse the software. Okay, so we've established the uppercase world of resistors. Let's look at the other major component crowding these circuit boards, capacitors. They seem to flip the script entirely.
They do. To differentiate themselves at a glance, capacitors generally rely on lowercase letters. You will see P for picofarads, N for nanofarads, and M for millifarads. The only major exception is F for farad, the base unit, which remains capitalized.
But even within this lowercase system, they ran into another typographical wall.
You're referring to the U workaround.
This one is my favorite because it feels so scrappy. The standard prefix for micro, as in microfarad, which is an incredibly common capacitor value, is the lowercase Greek letter mu.
Yes.
It looks like a U with a long tail on the front left side. But again, just like omega, mu was a nightmare to print, type, or render on early computer systems.
So the standard officially sanctioned a very pragmatic substitution. If a system cannot handle the Greek letter mu, you are allowed to just substitute it with a standard Latin U, either lowercase or uppercase.
Wow.
And this wasn't just an isolated decision by the IEC. It aligned with other early data processing standards like ISO 2955 back in the 1970s. They also authorized UP as a stand-in for mu when dealing with basic Latin-only text terminals.
It's amazing how much of this highly technical standard is basically just generations of engineers saying, look, our typewriter doesn't have that key. Let's just use a letter that looks close enough so we can go home.
It is the very essence of engineering, finding a reliable, robust solution within the strict constraints of your available tools.
Absolutely.
But if we connect this to the bigger picture, the RKM code isn't just about printing legible text on tiny parts or avoiding bad photocopies.
Right.
As the industry digitized, this alphanumeric shorthand revealed a secondary, almost secret benefit. It functions as a logistical superpower.
A logistical superpower. That's a strong claim. How does swapping a dot for a letter give you a superpower?
Because it completely transforms how parts are handled in bulk databases. Imagine a modern manufacturing plant. They are building complex electronics with tens of thousands of different tiny components.
Okay.
They organize all of this inventory using a massive database called a bill of materials, commonly known as a bill and bohm. Sorting a bill of materials is where the RKM notation truly shines as a data management tool.
Wait, let me see if I can follow the logic here based on the source text. Let's say you're an engineer and you have a raw list of standard resistance values for a new device.
Right.
You've got a 3.3 ohm resistor, a 3.3 kilo ohm resistor, a 3.6 kilo ohm resistor, and a 4.7 kilo ohm resistor. In a standard dumb spreadsheet that doesn't natively understand engineering units, if you just sort purely by the numbers, things are going to get incredibly messy.
Exactly. Because a standard text sort will look at 3.3 and group it with 3.3 kilo. It ignores the attached word kilo.
So your 3.3 ohm resistor gets sorted right next to a resistor that is 1,000 times more powerful just because the prefix numbers match.
It separates components that should be grouped, and it makes scanning the database a chaotic experience.
But look at what happens when you convert those values into the RKM code before you hit the sort button.
Yep.
The 3.3 ohm becomes 3R3.
Yep.
The 3.3 kilo ohm becomes 3K3. The 3.6 kilo ohm is 3K6, and the 4.7 kilo ohm is 4K7. Now, when your computer database sorts this list alphanumerically, it's beautiful.
The R values group together.
And all the kilo ohm values, 3K3, 3K6, 4K7, are locked together by the K, perfectly arranged in ascending order.
It forces the database to behave intuitively. And why should you care about this? If you are a supply chain manager handling millions of dollars of inventory, this sorting behavior is invaluable.
It allows you to scan a massive spreadsheet and instantly spot redundant parts.
You might look at your cleanly sorted list and say, wait, why are we buying 10,000 3K3 resistors and 10,000 3K6 resistors? Can we just adjust the electrical design slightly to use the 3K3 for both?
Oh, I see. By optimizing your inventory like that, you reduce the number of unique parts you have to source, buy, stock on shelves, and load into the automated assembly machines.
Exactly.
That saves a tremendous amount of money and overhead. It's
Yeah.
an accidental database optimization tool that was invented decades before supply chain databases were even a thing.
Precisely. And because it was so undeniably useful, the notation couldn't be contained just to resistors and capacitors. It naturally bled into all sorts of other areas of electrical engineering.
Right, like inductors.
Yes, inductors, which are coils of wire used in circuits, adopted it. You might see an inductor labeled 4R7, which would mean 4.7 microhenries. And even more surprisingly, the system was co-opted for expressing voltages.
Right, the source mentions this. When you are writing a schematic on a computer, or naming a digital file for a circuit design, or even assigning a label to a tiny pin on a microchip, a standard dot can completely break the computer code.
In software, a dot usually indicates a file extension.
Or a command in an object-oriented programming language. So you can't name a software variable 3.3 volts.
The compiler would crash trying to read it, so instead, engineers use the RKM style and simply write 3v3. No dots, no spaces, just 3v3.
And there's another variation for voltages in the text that I found really interesting. Sometimes instead of a V, you will see a P used as the decimal separator. So they might write 1P8 to represent 1.8 volts.
The P in that context typically designates a positive voltage or indicates a specific power supply rail on the board,
It serves the exact same function.
eliminating the fragile software-breaking decimal point while conveying essential technical information in a clean, machine-readable format.
Okay, so we've got the base values, we've got the multipliers, we've got the voltages. But if you look at a full component code, there is often more printed on these tiny parts than just their core value. I want to dig into tolerances, because this brings in a whole different layer of history.
Tolerance is a crucial concept in manufacturing. It essentially tells you how precise the component actually is. When a factory makes a 100-ohm resistor, it is rarely going to be exactly 100.00 ohms.
Right, the manufacturing process always has slight variations.
Exactly, it might be 101 ohms or 99 ohms.
So the RKM standard tacks on additional letters at the very end of the code to indicate this tolerance percentage. And they assign specific letters of the alphabet to represent different percentages.
For example, if you see the letter F at the end of a code, it means the part is highly accurate, guaranteed to be within plus or minus 1.0% of its stated value.
But if you see a J, it means it's a bit looser, within plus or minus 5.0%.
What's truly fascinating here is the embedded history of those specific tolerance letters. The Standard Committee didn't just pull them out of thin air in 1952.
Where did they come from?
Many of these symmetrical tolerance letters, specifically G, J, K, and M, actually stem from mid-1940s military specifications.
Oh, the source mentions the American War Standard and the Joint Army-Navy specification.
Yes, the AWS and JN specs. These were rigorously developed during World War II to ensure that military equipment, from radar systems to field radios, could be mass-produced with interchangeable standardized parts across different Allied factories.
Wow.
So when you look at a modern circuit board inside your smartwatch today and you see a J indicating a 5% tolerance, you are actually looking at a direct linguistic descendant of World War II military logistics.
That is wild. It's like finding an industrial fossil sitting inside your smartwatch. But the code still doesn't stop there. The source notes that letters can also denote things like temperature coefficients. Now, to make sure we are all on the same page, a temperature coefficient basically measures how much the part's electrical value shifts as it physically heats up or cools down. It's measured in parts per million per Kelvin.
And this is incredibly important. Imagine you are building a precision medical sensor that monitors a patient's vital signs. As the device runs, the electronics naturally heat up.
And if your resistors change their value wildly as they get warm,
The entire calibration of the device shifts, and the machine might give a doctor a false reading.
so knowing how stable the part is under heat is critical. And again, I use a letter code for that. But the part of the code that I found the most amusing deals with production dates. Here's where it gets really interesting. How do you encode the exact date a microscopic part was made using just a couple of characters?
The date codes are a brilliant, if slightly chaotic, study in human factors engineering. To track when a component was manufactured, the standard uses a repeating 20-year cycle represented by letters and numbers.
But they didn't just use the alphabet straight through from A to Z. Because humans are the ones reading these microscopic codes, often in poor warehouse lighting.
Or staring at components that have been running in a hot machine for 5 years.
Exactly. The architects of the standard deliberately banned certain letters to avoid visual confusion. They removed the letter G because on a tiny component, it looks entirely too much like the number 6.
They removed I because it looks like a 1.
And Q and Z were banned because they look like 0 and 2.
Which is perfectly logical. You want zero ambiguity on the factory floor.
But then the source text reveals this absolutely hilarious contradiction about how they encode the specific months of the year. So in the date code, the first character is the year and the second character is the month. For the months, digits 1 through 9 obviously represent January through September. But what do you do for October, the 10th month?
You can't use the number 10 because that requires 2 characters, and space is the most valuable commodity on these components.
Right. So they decided to switch to letters for the final 3 months. And for October, they chose the letter O.
Which is incredibly counterintuitive given the rules we literally just discussed.
Exactly. The letter O was famously on the banned list for the years because it looks exactly like a 0. So why on earth would they use it for the month?
It's a great question.
Well, the source text explains they did this specifically because October is the 10th month. The number 10 contains a 0. The logic was, if they used a different letter that happened to look like a 1, a technician might confuse it with January, the first month.
So by using O...
By using O, even if the technician's brain misreads it as a 0, they still associate it with the 10th month, effectively preventing it from being confused with the start of the year. It is this bizarre, twisted psychological logic that somehow works perfectly in practice.
Following that, November naturally becomes N and December becomes D.
It is a wonderfully pragmatic contradiction. They willingly broke their own cardinal rule of typography to solve a very specific human error problem regarding the calendar.
I just love the mental gymnastics behind that.
Me too. Now, before we wrap up, we have to touch on what happens when things get truly microscopic. Because technology hasn't stood still since 1952. We are talking about components today, like surface mount resistors, that are barely larger than a grain of sand. For these, even the standard RKM shorthand is sometimes too long.
Yes. When you simply do not have the physical real estate for 3 or 4 characters, the industry relies on standard preferred values, commonly known as the E-series.
Let's break that down for a second. The E-series is basically the industry's master list of standard values, right?
Right.
It exists so manufacturers don't have to endlessly produce a 100 ohm resistor, a 100.1 ohm resistor, a 100.2 ohm resistor, and so on. They just produce a set spacing of values that cover all the necessary bases.
Precisely. It is a logarithmic scale of preferred values. And because engineers know these exact values are standardized across the globe, modern updates to the standard, like IEC 600, 62.20, and 16, allow them to compress the code even further.
By using a specialized lookup table.
Exactly. They drop down to a highly compressed 3-character code for tiny resistors, which usually involves 2 digits representing the base value from the table and 1 letter for the multiplier.
And for microscopic capacitors.
They compress it down to an almost impossibly dense 2-character code. They squeeze out every single drop of unnecessary ink.
So what does this all mean? We started today by looking at a tiny, easily ignored string of characters on a circuit board. And we ended up uncovering a masterclass in pragmatic engineering.
It really is.
The RKM code isn't just an arbitrary set of rules forced on manufacturers. It is a deeply evolved global language. It was invented simply because physical decimal points are too fragile for reality, and mid-century photocopiers were unreliable.
It's a language built to survive the harsh, gritty environment of the factory floor.
To tame the chaos of supply chain databases.
And to work around the limitations of early computing keyboards. It really is a testament to how practical problem-solving creates lasting, invisible infrastructure.
It's incredible to think about.
And it leaves you with something fascinating to consider long after we wrap up today. This entire globally adopted shorthand, spanning from World War II logistics to the motherboards in our most advanced AI supercomputers today, is entirely defined by the physical limitations of mid-20th century tools.
Yeah.
It makes you wonder, as we move into the future of computing, will entirely new paradigms, like quantum computers, still be forced to inherit and use these exact same 1950s typewriter shorthands simply to remain backward compatible with our massive, deeply entrenched global supply chains? Are we locked into the letter R forever?
No. That is a wild thought to end on. Imagine a futuristic quantum array still using an R, because someone's typewriter in 1952 didn't have an omega key. Thank you so much for joining us on this deep dive. We hope you never look at a broken radio or a piece of modern electronics the same way again. We'll catch you next time.